And the next speaker is Debabrata Goswami from IIT Kanpur. And he's going to talk today about the quantum information processing with femtosecond laser-induced control.
Am I audible?
Yes, please go ahead.
Thank you. Thank you. I'm sorry, I missed my slot. It so turned out that we have a very high sudden rise of COVID, and there's a huge shortage of everything, including the vaccine. And somehow my second dose was possible to be received today, and they made a very quick notice. I had to go, and it was a huge rush, and a 15-minute affair turned out to be 2 hours. So I'm sorry I missed my schedule, but as it was very kind of the rescheduling to be able to come back and talk to you about what we are doing. So here is the basic principle in which I'll try to say. I'm going to focus a little bit more on the experiments if possible, and but let me start off with the kind of thing that I'm going to talk to you about. So, uh, so this is partly what I have given as my short summary of what I presented, and hopefully you have it in your abstract book, which says that we are going to talk about quantum information processing based on the idea of controlling quantum processes and in trying to avoid decoherence. And one of the approaches in this direction, which we have been pursuing for several years, is with using shaped ultrafast laser pulses. Our technology is something which uses an acoustic modulated Fourier transform pulse shaper, which I will explain. And it also has the capability to modulate at a very rapid rate, which is kind of something which is unique, and I will explain why this becomes useful. Now, and so this is the basic point. Let me first try to explain as to what we mean our approach. So, in general, you have been exposed to quantum computing a lot, so I don't think I need to show this slide to this community, but just for completeness, this is what we have. Whenever we can manipulate quantum systems, we call it quantum information processing, and anything that can lead to information processing that is useful in computing science, that is a quantum computing application. One of the biggest problem we have in quantum aspect is the idea of decoherence, is because although we have that great power, we do not really have a way of controlling how fast they will, how soon they will decoherence, so that they will maintain their coherence, and without that we have a problem. So this is the basic background behind this. One of the things which I would like to also point out here is that since we go into not a single photon kind of a scenario, when we have too much of photons available, it is perhaps imperative to understand what would happen if there are also multi-photon processes which can simultaneously occur. And one of the cases that I have referred to in this particular case, which is a useful condition for still carrying out quantum processes without any difficulty, is the specific case when either or happens, in the sense that either you'll have a single photon process, and that is maybe theoretically you might think this is not uh, typically what happens, but generally if you think about it experimentally, you are generally having photons of certain frequency or energy. So for example, I have a laser of, let's say, 800 nanometer light, and I have a energy gap which is of equivalent to the half, to 400 nanometer, which requires two photons of that. Now, unless and until I really have those two photons, I will not be able to inducing any single photon transition. Under that condition, you can create a situation where those two particular states will still remain as a two-level system under the two photon limit. And this is a very interesting approach to make a simple two-level argument extend into multi-photon case, under the presumption that a single photon condition cannot happen, and there it is possible to readdress what we talk about in a single photon condition very easily by just redefining certain terms, and that is what has been done. Before I started this entire process, we presented this in one of my earlier reviews, and this is with that logic, you can simply solve the Liouville equation and go ahead and see how things happen. So here are a few very quick theoretical background on this area, and you are welcome to refer to my review article whenever if you would like to. And so generally what happens is that you can under this condition, you can write down the Hamiltonian in such a way that you can readdress the two level system easily from carrying forward from a single photon principle, but using multiple photon idea. And based on that, you can see the concept of the intensity based effect, which is, as we know, is the Rabi oscillation and other kinds of things as we have been talking about in terms of light matter interaction. Okay. But there is one important thing which is important to know at this point, which is that Rabi oscillation is great, and in fact, Rabi oscillation typically is also not that easy. It's a coherent induced process where if there are averaging or any other effects happening, as we all know, it will almost always lead to saturation, and you will not be able to see the nice oscillating feature between the ground and excited states. So that in itself is an issue. But even then, the other important thing is for qubit operations is often not the most preferred situation. You would rather want to know whether you have the condition of being 0 or 1 rather than having an oscillating feature. So uh, uh, to be able to create a condition where you have very well specified zeros or ones in terms of, let's say, population distribution is one of the parameters which you are primarily interested. And if you would like to uh, work in an experimental condition, you would also want to be careful in making sure that your system is not extremely sensitive to any changes in say any changes in the terms of say frequency homogeneity or means inhomogeneity if there is a bandwidth associated with it, or many other parameters which may come making sure that you are unable to reach the 0 or 1 condition. So it is sometimes useful to take what the NMR people have been doing all the time, is to use the adiabatic concepts, where instead of using a regular pulse, you use a pulse with certain kind of shapes, and that can give rise to the inversion processes, which is under adiabatic conditions. And you can show that you would definitely go between cycle between, you can definitely decide to be either in the ground or the excited state. So that is a total inversion versus coming back to the ground state situation. So this is one of the things which extending it to short pulses is important, because in an ultra short pulse, as we know, there's large bandwidth, and so anything that we would like to address as a single frequency condition does not work for an ultra fast laser. The delta function scenario is not something which you can achieve when we are looking at a ultra short pulse, and that has consequences when you are looking at systems where there is a possibility of a large number of systems being interacting, or worst case when you have a molecule. And the other side of the story is if you go shorter and shorter, then you would be having the difficulty of getting into the few cycle pulse regime, which is what we are not talking about at this point, because we are using the rotating wave approximation. The rotating wave approximation allows us to use the envelope profile of the pulse rather than the oscillating feature coming into the picture. And we have also worked in this area where we have gotten into the ultra short pulses where your envelope profile is approximation. I mean, rotating wave approximation does not work anymore, and there we have to argue how it works. But generally speaking, there is a interesting scenario which we found that even for the cases where you are close to say when your pulses are fairly short, and you may otherwise be in the condition of a few cycle limit, the center part of the pulse can still often satisfy the uh, the conditions which are necessary for rotating wave approximation, but it doesn't work if you go to the edges. And those are the beyond rotating wave approximation cases. In this talk, I have avoided specifically those areas to be discussed, but that's a different kind of things that can be looked at. But generally speaking, what we are talking about is the laser projectile, where we can safely use the laser as the cosine as a in the semi-classical mode by not using the photon principle in that sense. We can have the interaction with respect to the field with the and therefore take the rotating wave approximation and see how the system interacts and the photon properties, the state properties, the population properties, and the coherences of the states, how they behave. So that is what we are looking at. When you go to a molecule, this actually extends to the concept of using a wave packet, which means that instead of using a single wavelength or a single frequency, as we call it, it will have a distribution. And there again, it so turns out that when you are using a transform limited pulse, which means that you will be having a large number of states instead of having a single eigenstate, you will have a distribution which is often called the wave packet, which spreads out because of the harmonicity or the round trip time is different for different energies. So this is the typical scenario for the wave packet picture. And there too, you can prove that it's actually interesting to come up with the modified pulses instead of using a regular Gaussian pulses which are transform limited. You could have so there the you can see the distribution in the wave packet, for example, is interfering and they spread out or they they have a large distribution which is all over the place. But you could in fact have a um, um, particular shape of a laser, which is no longer, let's say, nice like in Gaussian, but has some different looking shape, which can end up producing a very sharp looking profile at the end. And these can be useful because then you have a well-defined state in the excited condition, which you are looking for. Otherwise, you will be having a superposition which you have no control of. So that way, preparation of state with shape pulses are also very interesting and useful. So here is the example that we were able to show theoretically in earlier days as to how you could take a pulse into the excited state and can create wave packet recurrences. And it also has advantage in terms of measuring them because you can then easily find out how they look. Otherwise, when they are getting spread out, its population is probability goes down drastically. And all of these are based on principles where we devised the Hamiltonians in the sense that they incorporated a general class where you could use multi-photon as well as a single photon limits. And depending on the connectivity of the different states, you'd be writing out a Hamiltonian of this sort, which can then mimic molecules or systems which are heavily coupled, and you can then come up with ways of how to beat the decoherence coming up because of other states being close to each other. Or this could also mean that when multiple two-level systems are close to each other, they would also end up producing Hamiltonians of this kind. So irrespective of how you look at the problem, whether you are looking at a molecule of this sort, which is going to show heavy decoherence in terms of the population leaking away, or in terms of several two-level systems which are going to just have couplings to give rise to a multi-level situation in some sort, which can also have a similar structure in the Hamiltonian. So irrespective of these, you will be having these scenarios. So we picked up a example case to study in the beginning stages to see how our approach of using a shape pulse can change or have can in fact stop this heavy beating or let's say decoherence between states. Now, this is a particular case which was chosen because it was an experimental verification which was possible early, which of Anker and Zuel's work, where they had shown that there was accidental overlap of only a few states, and the energy was able to go back and forth, and so they were able to show very nice correlations between the states population going up and down. So it was like a quantum beating which they were able to show. And so we addressed this particular system, and we could find out a Hamiltonian which mimicked quite well to the experimental data. And when we looked at it, we were able to show that in case, indeed, if we do not use a simple Gaussian pulse but a shape pulse, so this is a solution that we had solved at that time, showing that if you take a pulse which actually has a profile, which has a frequency, maybe the perfect case is to have the frequency go up slowly. So this is a simple case of, in the simplest form, you're sweeping up to the resonance, holding it there, and then coming back. This is the adiabatic half passage in the classic sense. And then you can, in fact, have this particular perfect, the population getting locked into the state 1 and state 2, whereas all these other states are not participating. And you can have this beautiful locked condition, and once the frequency turns off, tapers off, you also see it going down. That's one way. But then the more practical case perhaps would be to take, if you have a linear chirp, which is experimentally viable, and see if this will be possible. Because a frequency sweep going up and doing all this is horrendously difficult. And I don't know if we can really mimic that, but definitely we can do variants of linear chirp. And so it was also found that for a, if this chirp is slow enough, linear region also, we could perhaps generate a region over which it was possible to lock it. So this was the deep blue color one, which goes like this, and then it goes on the other side. So it was possible to track it for at least a little while.
The last seconds, please. The time is almost up, so if you can wrap up, that will be excellent.
Okay. So I would like to now perhaps go faster and say that we have managed to show these kinds of coherent interactions between states quite a bit. Now, what I would then want to go and present to you now, by the way, linear chirping is very simple. It was often, this is the Nobel Prize work of Rana, who I had worked with when I was a graduate student in the same lab for a while. But other than that, I would want to go and show you that the principle that we use is a molecular beam chamber. That's the simplest case, where you can address one molecule at a time and can do these experiments. And we have managed to show that it's possible to use a chirp pulse to do these kinds of interactions in studies. One thing which is important is to know how this works. So this is a simple chirp is easy, but if you'd like to do something more than that, a programmable one, now that's where you have to actually go through a principle which is different. Conventional electronics doesn't work because they work in nanoseconds, so you need optical help, and this is where we use a Fourier transform and reverse Fourier transform. In the Fourier plane, we use an modulator which actually programmable, and you can do a shape based on that. So based on that, we have managed to do pulse shaping. This is a technology where you can pick up the right function at the right time, and at the rest of the time you don't need to know it. So often something called a Pockle cell does the job for you. But the difficulty is that this works at a rate which is comparatively slow. So you can go up to a kilohertz with it, and for molecular systems it's fine. But if you are going to go away from this principle of using a gas vacuum chamber based system, you want to do this in, let's say, in liquids, this will not work. And there you would like to add spatial control, which is by using optical tweezers, which is what Ashkin's work is all about. So what we have done is we have actually done pulsed optical tweezers, which allows you to produce trapped particles with the pulse laser. And then when the pulse is, particle is trapped, you can use the shape pulse to address and do interactions with it. So the advantage of pulse laser anyway in trapped case is that it can automatically show you its nonlinear process right away by using without using any other laser. So a single pulse can do the job for you. And what you need then is a high rep rate thing. So the same technology, which only works for low rep rate, can now, we changed that recently. So this is the old one which I just showed you, which is slow. But if you like to, if you do it in a way so that you can do it. So here's a big slide which should tell you. Okay, so I'll show you. This is the case. What happens now? If you let it interact free flowing, you still see that you do not get all the shapes which are correct, but you do get certain shapes which are correct. All you need to do is now to be able to catch the ones which are the right shape. So the two problems are then different. One is to allow the shape pulse syncing at time steps, which goes only up to a kilohertz. The other option is to let the traveling wave interact, and the ones that are correctly shaped, you pick them up. How do you do that part? Is picking up of the shape in the right time. There is no switch which can work that fast. So what we used is again the Fourier argument. You give a phase delay in the Fourier domain. So otherwise it looks like that all in the same place. You cannot distinguish between the shaped pulse as well as the one which is unshaped. But if you give it a phase delay in time, in frequency domain, then you will see a time delay. And so what you can do is you can actually do a time delay to the pulse by giving a Fourier phase, and so you get your shape pulse with respect to your original pulse, which is time delayed now, and that is your purely shaped pulse that you can use to do your activity. So not only do you have an optical pulse to create your tweezer, but you also have your shape pulse to do your logic. So that is the idea, and that's what
Okay,
we are
thank you.
working on. Yep. So,
I think time is up, so I would like to thank once more to Debabrata Goswami also for this talk. And also I would like to thank everybody in the session for joining us.